Welcome to the Chemistry, Biology and Math Revision Hub. Today we're doing the Pearson Edexcel International A-Level Chemistry Unit 1 for May 2023. Let us begin with the first question. Question 1 says, which compound has the greatest covalent character? Of course, to have greatest covalent character, you should have the greatest charge density. And since magnesium has a higher charge than sodium, so sodium is ruled out. Now, fluoride is smaller, but bromide is bigger, so it means because the anion is bigger and the cation is smaller with a bigger charge, it means the bond between magnesium and Br is going to have the greatest covalent character, and therefore it's going to be my answer. In question 2, they say which has the smallest ionic radius. All these have the same electronic configuration, but if you can see magnesium has more protons, it means the outer electrons are going to be attracted more, and therefore it's going to have the smallest ionic radius. So B is going to be my answer. In question 3, the first 7 ionization energies in kilojoules per mole of an element are shown. They say in which group of the periodic table is the element located. So when you look at the first 5 ionization energies, we can see the change is not that drastic. So there is no bigger gap between these two, no bigger change, no bigger change, no bigger change. But we can see from 6,270 to 21,000, there is a big gap. That is actually the first bigger gap. So we can say 5 electrons were in the outer shell, and this is going to be a group 5 element. So my answer was C. If you go to question 4, they say what is the electronic configuration of an oxygen atom in its ground state? Oxygen has 2 electrons in the inner shell and 6 electrons in the outer shell. So the configuration is going to be 1s2, 2s2, 2p4. However, the p electrons are going to be 2 electrons in the 2px, 1 electron in the 2py, and 1 electron in the 2pz. So D is going to be my electronic configuration. For question 5, which property shows a general decrease across the periodic table? Atomic radius, this is true because it's the same number of shells. However, the number of protons is increasing, so the attraction from the nucleus to the outer electrons is going to be increasing, and that means atomic radius decreases. Electronegativity, this is going to increase from left to right. First ionization energy also increases, and melting temperature will increase and then decrease, so the answer should be A. In question 6, the first ionization energy of sulfur is lower than that of phosphorus. And again, here we can see I tried to put the configuration of sulfur. We have neon, 3s2, 3p4, and then there is pairing here. And then for phosphorus, we have neon, 3s2, 3p3, which is going to be in that manner. So it means here there is no pairing, while there is pairing here. So due to repulsion between the electrons in the same orbital, it's going to have a lower first ionization energy. So I said the repulsion between the outer electron of sulfur is greater than that of phosphorus, so the answer should be a C. Question 7. 1 kilogram of seawater contains 64 milligrams of bromide ions. They've given us the AR of bromine atom as well as Avogadro's constant, and they say what is the concentration of bromide ions in parts per million by mass. So since they've given us 1 kilogram of seawater contains that, 1 milligram is 10 power negative 3 grams, so 64 should be 64 times 10 power negative 3 grams. So the concentration of bromide ions should be the mass of bromide ions divided by the mass of seawater times 10 power 6, which gives us 64 ppm, so my answer should be B. In part B, how many bromide ions are in 500 grams of the sample? Remember from the sample, 1 kilogram of seawater contains 64 milligrams of bromide. So in 500 grams, which is going to be half a kilogram, it's going to be 64 divided by 2, which is 32 milligrams. And that is going to be 32 times 10 power negative 3 grams if I convert that to grams. So the moles of bromide are going to be the mass of bromide divided by the AR, which is 80, giving us 4 times 10 power negative 4 mole. And this, multiply that with Avogadro's, is going to be 4 times 10 power negative 4 times 6.0 times 10 power 23. Remember here they gave us 6.0. So I got 2.4 times 10 power 20 bromide ions, and A was my answer. In question 8, 0.15 mole of aluminium is added to 120 centimeters cubed of 1.5 mole per decimeter cubed hydrochloric acid. So this is the equation for the reaction, and they say the amount of unused reactant is From the question, we have the concentration and volume of HCl, and this is given in mole. So I'm going to begin by calculating the number of moles of hydrochloric acid, which is going to be concentration times volume, giving me 1.5 times 120 divided by 1000. This is converting it to decimeters cubed, and I get 0.18 mole. So we can see 2 moles of aluminium must have reacted with 6 moles of HCl, so the mole ratio is going to be 1 to 3. However, in this reaction, aluminium is reacting with H plus in the ratio of 0.15 to 0.18. This is equal to 1 to 2.4, and we can see in this experiment, aluminium is going to be excess. Since all the H plus is used up, it means the acid was the limiting reagent, and therefore I can use the moles of the acid. So the moles of aluminium are going to be 2 divided by 6 times the moles of the acid, which is the same as 1 over 3 times the moles of the acid, giving me 0.06 mole. So the moles of aluminium that remained are going to be the moles that were there initially minus the moles that have reacted to give me 0.09 mole of aluminium, and my answer is going to be a B. Question 9. An organic compound contains 24.2% carbon and 4% hydrogen and 71.8% chlorine by mass. So they've given us the atomic masses of each. What is the empirical formula of the compound? Here I calculated the number of moles of each by using the percentage composition. So 24.2 divided by 12, 4 divided by 1, and 71.8 divided by 35.5. And these are the number of moles I got. Then I divided through to get the mole ratio. That divided by that, it gave me 1. That divided by that, it gave me 1.9. And that divided by that, it gave me 1.0029. So this is roughly 1 to 2 to 1. And the empirical formula should be 1 carbon, 2 hydrogens, and 1 chlorine. So B is going to be my answer. In question 10, which solution contains the smallest number of ions? The moles of ions are going to be the concentration times the volume, and that gave me that, times the actual ions, which are 1 calcium and 2 nitrate, which is times 3. Of course, I did not multiply Avogadro's constant because it's going to be the same for all, so I just took the part that should have been multiplied by Avogadro's constant. So this is going to be 0.09 mole. And then for this, we're going to have 0.09 times 500 divided by 1000 times 2, because we have 1 potassium and 1 iodide, so times 2. It gave me that. For this one here, we have the concentration 0.12 times 250 divided by 1000, but the ions are barium 1 and 2 chlorine, so that's total 3. I got that. Then here we have 0.09 times 250 divided by 1000 times 1 sulfate and 2 ammoniums, which is going to be 3, and this gave me that. We can see the rest was 0.09, but these had less, so my answer should be a D. In question 11, a piece of filter paper is soaked in water and attached to a microscope slide. A few crystals of green copper 2 chromate are placed in the center of the filter paper. The filter paper is connected to a DC supply of 20 volts. What colors are observed on the filter paper after a few minutes? Now, in the copper 2 chromate, there is going to be copper 2 plus a cation, and there is chromate, which is yellow, and then an ion. This is blue. So because this is positive, it's going to be attracted towards the negative electrode. So copper will be formed here, or a blue color is going to appear here. So that will be blue. And this yellow color is going to appear at the positive electrode. So my answer should be yellow here and blue here. And this should be my answer. In question 12, the melting temperature of beryllium is greater than that of barium. What is the best explanation for this statement? When we melt metals, we are breaking the metallic bond. However, the strength of the metallic bond depends on the charge of the cation as well as the size, because if a cation is small and has a higher charge, the length of the metallic bond is going to be shorter, and therefore the bond is going to be stronger. So my answer here is beryllium ions are smaller than the barium ions. In question 13, which molecule has the largest bond angle? So of course this is a triagonoplanar, which is 120 degrees. This one here is tetrahedral, we have 109.5. This one is 104.5, and this is 107, so it's going to be this one, which is 120. In question 14, which molecule is polar? We see carbon dioxide, the bond is polar, however it's symmetrical, so that whole molecule is non-polar. Here we have polarity, but the dipoles do cancel out, so that is out. in here, the dipoles don't cancel out, so the answer is going to be a C. Sulfur dioxide is going to be polar. In question 15, the reaction of methane with chlorine is a free radical substitution. Which termination step does not occur? There is no termination step involving hydrogen or a hydrogen-free radical, so this is really, really wrong. The answer should be a C. The rest of them do occur. There is a methyl radical and a methyl radical. There is a methyl radical and a chlorine radical, and chlorine radical and chlorine radical. So this is the only one that is wrong. In question 16, the repeat unit of a polymer is shown, which is this one here, which is the name of the monomer that forms the polymer. The monomer should have been when the double bond is here, and these extensions are not here, as we can see here. So taking the longest chain to be 1, 2, 3, 4 carbons, this is going to be a methyl group on carbon 2, so we can say it's a 2-methyl butane, and C was my answer. Question 17, what is the IUPAC name of the compound shown? Now again, this was not like this. I just placed the carbons there. They were not included. I placed them there so that we can visualize the longest chain. So to know this IUPAC, it's going to be 1, 2, 3, 4. Remember, this is the functional group as well as this, so they have to be included within the main chain. So bromine has to be attached directly to a carbon within the main chain, and that's why I'm taking this to be my main chain. And this is going to be carbon 1, so we have a 1 bromo, and then we have a 2-methyl. So 1 bromo, 2-methyl, and this is going to be a but1-ene, so it's going to be an E, 1 bromo, 2-methyl, but1-ene, so A is going to be my answer. Question 18, they say the skeletal family of cyclohexa 1,4-diene is shown. The total number of sigma bonds in this molecule is. I extended out the bonds to show the hydrogens. So on this carbon, we have 2 hydrogens. Here we have 1, here 1, here we have 2, here 1. And of course, this is going to be 1. So the sigma bonds are 1 here, the second, the third, fourth, fifth, 6th, 7th, 8th, 9th, 10, 11, 12, 13, 14. So the total is going to be 14, and my answer is D. In part B, 1.6 grams of cyclohexa 1,4-diene is reduced to cyclohexane by reacting it with hydrogen gas. The molar volume of gas is 24 decimeters cubed per mole at room temperature and pressure. They've given us the MR, which is 80, and they say what is the minimum volume in decimeters cubed of hydrogen needed at room temperature and pressure. So because this has 2 double bonds, it's going to react with 2 moles of hydrogen to produce the cyclohexane. And the number of moles, if this is the mass, number of moles should be 1.6 divided by 80, giving us 0.02 mole. Now, the moles of hydrogen needed are going to be twice of that. So 2 times 0.02, which gives us 0.04 mole. And the volume of hydrogen produced is going to be number of moles times molar gas volume, which is 0.04 times the 24 decimeter cubed per mole, giving us 0.96 decimeters cubed. And this is going to be my answer. So moving on to section B. Question 19, this question is about mass spectrometry and the shapes of molecules. In a mass spectrometer, vaporized atoms are ionized and the ions formed are accelerated, deflected, and detected. State how atoms are ionized in the mass spectrometer. Of course, these are going to be ionized by bombarding them with a beam of high-speeding electrons. These speeding electrons will knock off electrons from the gaseous atoms in order to produce gaseous ions. So here we have a gaseous atom interacting with a high-speeding electron. One electron is knocked out and a gaseous ion is going to be produced. Next, they say state how ions formed are accelerated. They are accelerated, of course, using the electric field, and this electric field has a series of negatively charged plates that are going to accelerate them. Next, they say explain why isotopes of an element have the same chemical reactions, but their ions are deflected differently in the mass spectrometer. Deflection in the mass spectrometer is based on the mass to charge ratio. So meaning, because isotopes have different atomic masses, of course their deflection is going to be different. So I said isotopes of an element have the same electronic configuration, so they have similar chemical reactions. However, isotopes do have different atomic masses. Since deflection in the mass spectrometer depends on mass to charge ratio, they have different M to Z ratios and are going to be deflected differently. Data from mass spectra may be used to determine the relative atomic mass of elements. They say state what is meant by relative atomic mass. A relative atomic mass is an average mass of atoms of an element, which is compared to 1/12 the mass of a carbon-12 atom. Next, they say a sample of chlorine contains 75.53% chlorine-35 and 24.47% chlorine-37. They say calculate the relative atomic mass of this sample of chlorine, giving you answer to 4 significant figures. So to find the relative atomic mass is going to be the percentage of this times 35 plus the percentage of that times 37, divide everything by 100, and I get 35.4894. Since they want my answer to 4 significant figures, I rounded off to 35.49, and that was my answer. Next, they say the mass spectrum of phosphorus trichloride, which is PCO3, is shown. Phosphorus has only one isotope, which is phosphorus 31, and we can see there is relative abundance as well as the corresponding mass to charges. They say there are 3 peaks in the region of mass to charge 101, 105. They say complete the table by showing the ions responsible for these peaks. So at 101, of course, we have phosphorus, which is 31. It's standard for all of them because it's just one isotope. All of them are going to have 31. So to get 101 is going to be a phosphorus 31, chlorine 35, and a chlorine 35, meaning there is one chlorine atom that is missing. So this is going to be the ion. And then for 103, we're going to have a phosphorus 31, chlorine 35, chlorine 37. And at 105, we're going to have phosphorus 31, chlorine 37, and chlorine 37. And of course, the relative peak heights are going to be, in this case, probability of having a 35 is going to be 3/4 times 3/4, giving me 9/16. So this is going to be 9 if you're talking about the ratio. This is going to be 3/4 for 35 times 1/4 for 37, but this is going to be twice. So this is going to give me 6/16. And then for this, it's going to be 1/4 times 1/4, which is going to be 1/16. So if you compare the ratio, 9 divided by 16 to 6 divided by 16 to 1 divided by 16. And again, this is a 16. I hope you can see it clearly. It gives us a 9 to 6 to 1. And that is the relative peak height we can see in there. So here they say show that the relative peak heights given in the table are consistent with the isotopic ratio of chlorine 35 and 37, which is 3:1. Yeah, this is true. And again, like I've done already in the table, at 101, we have a 35, giving us 9/16. At 103, we have twice, a 35 and a 37, giving us 6/16. And at 105, we have a 37, giving us 1/16. And this ratio is going to be 9 to 6 to 1, as we can see in the table. Then in part D, they say draw a dot and cross diagram of a PCO3 molecule. Show outer electrons only. This is easy. Phosphorus has 5 electrons in the outer shell. It's going to use 3 of those electrons to bond to 3 chlorine atoms, and then the 2 are not going to be bonded. Also, we can see each chlorine atom has 7 electrons in the outer shell, so here we're going to have 2 shared, 2 shared, 2 shared, and then a lone pair on phosphorus. Next, they say explain the shape of a PCO3 molecule. In a PCO3 molecule, we have 3 bond pairs and 1 lone pair around the phosphorus. The bond pair-lone pair repulsion is going to be greater than the bond pair repulsion, so the structure is going to rearrange itself into a pyramidal shape to minimize repulsion, and here the bond angle is going to be 107 degrees. So this brings us to the end of question 19. Let's continue to question 20. Question 20. Barium chloride can be prepared by the reaction of barium carbonate with hydrochloric acid, as we can see here. They say write an ionic equation for this reaction. State symbols are not required. When we write ionic equations, only the aqueous are going to be broken apart. So this is going to remain intact as barium carbonate, but this and that are going to be split. And since chloride is going to be on both sides, that is going to be a spectator ion, so it's going to be cancelled out. We remain with 2H plus here, and here we remain with barium 2 plus, and then the rest is going to be the same because it's not aqueous. The next they say calculate the atom economy by mass for the preparation of barium chloride. They've given us the AR values. Here, atom economy is going to be the molar mass of barium chloride, which is the product here, divided by the molar mass of all products. Or you could say molar mass of barium chloride divided by the molar mass of all reactants. So this is going to be for barium chloride, which is going to be barium plus the 2Cl. So 137.3 plus 2 into 35.5 divided by the molar mass of barium chloride, which is already the same as what we have here, plus CO2, which is 44, plus water, which is 18, and multiplying that by 100, so I got 77.1%, and this is my answer to 3 significant figures. That is the atom economy by mass. Next, they say barium chloride has a melting temperature of 962 degrees Celsius, and cesium chloride has a melting temperature of 646. Explain, by considering the ions involved, the difference between the melting temperatures of these period 6 chlorides. Cesium is bigger in comparison to barium, yet barium is a 2+ charged ion, so we can say barium is going to have a greater charge density in comparison to cesium. So polarization is going to exist between barium and chloride, and that is going to increase the covalent nature within the bond, making it harder to be broken. So I said barium 2+ has a smaller size and a higher charge than cesium+. So barium 2+ has greater charge density, and due to that, the attraction between chloride and barium 2+ is stronger than the attraction between chloride and cesium. So more energy is required to overcome the forces of attraction in order to melt barium chloride. Next, they say covalent and ionic bonding are the extremes of a continuum of bonding type. Explain the difference in bonding between barium chloride and beryllium chloride using the electronegativity values, which are shown here. So we have for barium, we have beryllium and Cl. I subtracted together difference between barium and Cl is 2.1, and between beryllium and Cl is 1.5. The difference in electronegativity in barium chloride is 2.1, while that in beryllium chloride is 1.5. So the bond between barium and chloride is more ionic than the bond between beryllium and chloride. We can see there is a greater difference in electronegativity, so this is more charged in comparison to that, meaning it's more ionic in comparison to that between beryllium and Cl. In part B, barium chloride reacts with group 1 sulfates. So we see that plus barium chloride gives us barium sulfate and MCl. A solution is made by dissolving 7.98 grams of a group 1 sulfate in deionized water. Excess aqueous barium chloride is added to this solution and the precipitate is filtered, dried and weighed. The mass of the barium sulfate precipitate is 10.72 grams. Identify the group 1 element. They've given us the atomic masses. So remember, this was excess, so this is going to be limiting and I can be able to use that mass. So using the information, the MR of barium sulfate, I can calculate it using that, which is going to be barium 137.3 plus the sulfur 32.1 plus 4 oxygens, giving me 233.4 gram per mole. So moles of barium sulfate produced are going to be mass divided by MR, which is 10.72 divided by 233.4, giving me those as the number of moles of barium sulfate produced. And again, remember, this was the mass obtained. So I'm going to work backwards. Using this number of moles, mole ratio of barium sulfate to M2SO4 is 1:1. So the moles of barium sulfate and the moles of the metal sulfate are going to be the same. Now we can work out the MR of the metal sulfate, which is going to be mass divided by number of moles, giving me 173.74 gram per mole. So to find out the component of M, it's going to be the molar mass of this minus the part of sulfate divided by 2, because whatever remains will be equivalent to 2M, so I have to divide by 2 to get the equivalent of M. So this is going to be 173.74 minus the part of sulfate, which is 96.1, divide by 2, and this gave me 38.8, which is approximately 39. And so the group 1 element is going to be potassium. So this brings us to the end of question 20. Let's continue to question 21. Question 21. Graphite electrodes are used in the extraction of aluminium by electrolysis of aluminium oxide dissolved in a solvent or molten in cryolite at a temperature of 950 degrees Celsius. explain how the structure and bonding in graphite make it suitable for this application. They want you to refer to the diagram. This is the structure of graphite. So graphite has a giant structure. It's arranged in layers. However, in graphite, each carbon atom is bonded to 3 other carbon atoms, meaning there is an extra electron, so conduction of electricity can be attained. And also because graphite is a giant structure, it's going to require a lot of energy to be melted, so it can be useful in these conditions where the temperature is up to 950. So I said graphite is a giant structure with multiple covalent bonds that require large amounts of energy to be broken, so its melting point is way above 950. Also, graphite can be used as an electrode because it has delocalized electrons. These can move when a potential difference is applied. In part B, the half equations for the electrolysis reactions are shown. So there is that as well as that. The oxygen produced reacts with the graphite electrodes, so we can see that. They want you to calculate the maximum volume in decimeters cubed of carbon dioxide measured at room temperature and pressure, which could be produced when 1 kilogram of aluminium is extracted using this process. The molar volume is 24 decimeters cubed per mole at room temperature and pressure. So I combined the two equations, these two, to create the overall redox equation. Since these electrons were 6 and these were 6, just combine the two and I got that. So the moles of aluminium are going to be the mass divided by the atomic mass. So 1 kilogram is 1,000 grams divided by 27, so those are the moles of aluminium. The moles of oxygen are going to be 1.5 divided by 2 times the moles of aluminium, and this is 1.5 divided by 2 times 37.037, giving me 27.778 mole. And now the moles of oxygen will equal to moles of carbon dioxide, which is equal to 27.778 because the ratio is 1 to 1. That last part is for this reaction here, because the oxygen produced is going to react with the carbon dioxide, which is the graphite electrons. So volume of carbon dioxide produced is going to be number of moles times volume molar, which is that, times 24. And I got 666.672, which is 667 decimeters cubed, to 3 significant figures. Next, they say every year in the UK, about 7.2 billion aluminium cans are recycled. Suggest 3 ways this recycling reduces energy consumption. Now remember, aluminium is obtained using electrolysis, and electrolysis requires a lot of electricity. So if we can recycle, it means less aluminium is going to be extracted from aluminium oxide and less energy is going to be used in that process. So I said less electrolysis to obtain pure aluminium will occur and less energy will be used to mine more aluminium. So the cans would be melted and this uses less energy than electrolysis. So I should write less energy. So this brings us to the end of question 21. Let's go to question 22. Question 22. Crude oil is mainly a mixture of saturated hydrocarbons that can be separated by fractional distillation. The diagram shows in a simplified form the products of fractional distillation. So we have the refinery gas, we have gasoline, kerosene, diesel, fuel oil, bitumen, and then this is the crude oil. In this case, it's going to be vaporized as it enters into the distillation column. They say state what is meant by a saturated hydrocarbon. A saturated hydrocarbon, of course, has no carbon-carbon double bonds. We can say it's a compound that contains only carbon and hydrogen atoms. That part is explaining about the hydrocarbon. And also, it's bonded only using single bonds. Next, they say describe how the fractions in crude oil are separated during fractional distillation. During fractional distillation, the crude oil is going to be heated, it's going to be vaporized, and the vapors are going to condense at different temperatures in the column. Those that have lower boiling points are going to condense at the top or will be collected at the top actually when they are still in gaseous form, while those that have lower boiling points are going to condense from a little bit lower in the column where they will be collected. In part B, butane is found in the refinery gases fraction of crude oil. It is used as a propellant in pharmaceutical inhalers. An inhaler that provides a total of 120 doses contains 1.55 grams of butane. They want you to calculate the volume in centimeters cubed of propellant used for each dose at 25 degrees Celsius and 100 kilopascals. They want you to use the ideal gas equation and give your answer to an appropriate number of significant figures. Using PV is equal to nRT, and R is given. So V is equal to nRT divided by P. Now the moles of butane, which is going to be N, is going to be mass divided by MR, which is the mass given here, 1.55 divided by the MR, which is 58. And these are the number of moles I got. The pressure given to us is 100 kilopascals, and we can convert that to pascals, so it's going to be 100,000 pascals. The temperature is 25 degrees. We add 273 to convert that to Kelvin. So V will be the N, which is that, times the R, which is 8.31, times the temperature, which is 298, divided by the pressure, which is 100,000. I got 6.6179 times 10 power negative 4 meters cubed. So I have to multiply this value times a million, and I got 661.79 centimeters cubed per 120 doses. Now each dose is going to be that divided by 120, and I got 5.5149166.7, which is 5.51 centimeters cubed per dose. And that was my answer. Here they say octane, which is that is found in the gasoline fraction of crude oil. They say write an equation for the complete combustion of octane and include state symbols. This is octane, and if it's reacting with oxygen, it's going to produce carbon dioxide and water. When we're balancing this kind of question, we begin by balancing the carbons. Since there are 8 here, and all the carbon in this ends up as CO2, I'm going to write 8 here to balance that. And since all the hydrogen here ends up in water, and this is 18, I'm going to put a 9 here to make that 18. What we remain with is going to be oxygen, which is 8 times 2, giving us 16. And the other side we have 9. So 16 plus 9, we get 25. And this is going to be 25 over 2, meaning the total is going to be 25 atoms of oxygen. Next, they say give 2 reasons why alternative fuels such as bioethanol are being developed to replace those produced from crude oil. Of course, they're going to be closer to carbon neutral. Also, biofuels are renewable, meaning we can grow the plants that are used to produce the biofuel continuously without worrying that depletion will occur or they will get finished from their reserves. Next, they say straight chain alkanes such as octane are converted into branch chain alkanes to improve the performance of petrol in car engines. Name this conversion process. The process is called reforming. And then they say give an equation using skeletal formulae of the conversion of octane into 2,5-dimethylhexane. State symbols are not required. This is octane, 1, 2, 3, 4, 5, 6, 7, 8 carbons. And 2,5-dimethylhexane should have 6 carbons in the main chain, which is 1, 2, 3, 4, 5, 6. And then there is a methyl on carbon 2, which is that, and another methyl on carbon 5, which is that. So this should be your answer. In part D, they say in steam cracking, a mixture of hydrocarbons and steam is heated to 850 degrees Celsius for a very short time in the absence of oxygen. Give a reason why oxygen should be excluded during steam cracking. There is a possibility that oxygen could react with the hydrocarbons to form other products of carbon like carbon dioxide and carbon monoxide, and this could decrease the percentage atomic economy of the desired product. Next, they say ethene is a major product. State one use of ethene. Ethene can be used to make polymers. It can be used to make other organic compounds like alcohols, for example, ethanol. And in part E, they say ethene reacts with hydrogen bromide to form bromoethane. Draw the mechanism for this reaction, and they want it to include Kali arrows and relevant lone pairs and dipoles. Now, I begin from here. This bond is polar, so this is going to be partially positive and that is partially negative. And due to that, the electrons here are going to be donated to the hydrogen that is partially positive, and that bond goes away or breaks, giving the electrons from the bond to be R. So we get this. This is a carbocation we form, and here we have the bromide with the 2 electrons from the bond. Then in the next step, this comes and donates the electrons to the carbon, like you can see here. This is the lone pair donated to the carbocation, and then in the end we get our product, which is going to be bromoethane. The key thing about this mechanism is the arrows have to be appropriate. It's the double bond breaking, giving the electrons here, and these have to be positioned. Then the positive on the carbocation has to be shown, and the arrow here has to come from the lone pair towards the positive carbon. So this brings us to the end of question 22 as well as to the end of the whole paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.